This is going to be our review session for exam 2, which is going to cover chapter 3 and 4 of Brown and LeMay book. So this is the 12th edition of the book, because sometimes I'll be referring to problem numbers, and I'm going to also write down the information given in that problem. There'll be question on, so this is review number 2 for exam 2, and that's going to cover chapter 3 and 4, Brown, LeMay book, and Burston. I'm going to give question on reaction type. Now there are several different reaction types: combination, decomposition, single displacement, and double displacement reactions. For example, if I'm giving you this reaction, Na plus O2 giving Na2O, 4Na O2. What type of reaction is this? This is a combination reaction, because I have one type of product. So when I have one type of product, that's combination reaction. Decomposition, you begin with one compound, but end up with more than one. For example, if you have a calcium carbonate, if you heat calcium carbonate, that will break down into calcium oxide plus carbon dioxide gas. This is decomposition. You are breaking down calcium carbonate into two products. So this is decomposition. Later on, we'll give you examples of single displacement and double displacement reactions, and there'll be questions on them too. Now, what kind of question I may be asking you? In a problem, I may not give you the formula. For example, say this question is given, and I would say sodium and oxygen reacts and gives a combination product. So in other words, I'm telling you that this is a combination reaction, and you need to find out what is the formula of the product. Since we know it's a combination reaction from the given information, I am going to write down first two elements side by side, sodium and oxygen. Then I need to figure out what should be the formula of this compound. Sodium is from group 1A. Remember, I said that group 1 I gets plus 1, 2A plus 2, 3A plus 3. So this is from group 1A of periodic table, so it gets plus 1. Oxygen is from group 6. So group 6 minus 8, that's minus 2. These are called oxidation numbers. So once I know these oxidation numbers of sodium and oxygen, then I can write down the formula. In writing formula, forget about these pluses and minuses. This 2 goes down here, 1 comes here. So basically, I know now that the formula of this compound is Na2O. So there will be a question like this in exam, where I would ask you to predict product of a combination reaction, or a single displacement reaction, or a double displacement reaction. Decomposition, there are very limited kinds. Carbonates usually break down into carbon dioxide and oxide. And unless I tell you, you don't need to balance it. Like I didn't balance it, I mean that's okay if I'm just asking you what is the product of a reaction. So I'm going to ask you what is the reaction type by giving you a reaction. Secondly, I would ask you to predict product of a reaction. It could be a single displacement, double displacement, combination, or decomposition. Now the third kind of question that I may give you would be percent element calculation in a compound. So I'll show you one example, and I'll do the calculation of percent carbon in C2H6. This is an organic compound, ethane, having 2 carbon, and I want to calculate percent carbon. So how do I get percent carbon? Percent carbon will be given by gram of total number of carbon. Gram of 2 carbon, because there's C2, so there are 2 carbon. Total mass on the bottom. And that total mass has 2 carbon and 6 hydrogen. So basically I'm talking about 2 carbon plus 6 hydrogen in gram. So let's now write down all these in gram times 100. Each carbon is 12.01 to be more exact. Now I'm rounding off here, so it's 2 times 12 divided by the total mass would be 2 times 12 plus 6 times 1, which is 1.008 for each hydrogen, but again I'm rounding off to 1. So at the bottom you have 30 times 100, so 24 by 30 times 100 is 80%. So in ethane you have 80% carbon. So these are straightforward problems, but I would like you to know how to do percent element calculation in a compound. The next type of problem, which would be on the test, has to do with gram mole or mole to gram conversion or mole to number conversion. So I'm going to go over a couple of examples. Let's assume that I have 36.0 gram H2O. Say I have a sample of 36.0 gram of H2O, and if I want to know how many H atoms I have in that sample. So how do I calculate H atoms? So start with 36.0 gram H2O. In my lecture notes, I have mentioned to you how do I go from gram to mole. So I say GMP, gram mole periodic table. So by looking at periodic table, you get the gram value. So this is the gram of water per mole of water. How do I get gram of water? By looking at periodic table, each hydrogen mass will be about 1 times 2 plus 16. So altogether you have 18. So you have 18.0 gram of H2O, that makes a mole of H2O. So gram would cancel out. This is a dimensional analysis problem. Now, 1 mole H2O. Each H2O has 2 hydrogens. So keep that in mind. So 1 mole of H2O would have 2 moles of H atoms. Don't get confused between mole and molecules, moles and atoms. This mole is a big number. Now, if I stop here, I'm going to get mole of H atoms. Now I need to get the exact number, so which is 1 mole H atoms. On the top you'd have Avogadro's number, 6.022 times 10 to the power 23 H atoms. I want to remind you that mole represents that big of a number, 6.022 times 10 to the power 23. Just like million is 10 to the power 6, 1,000 is 10 cubed. Similarly, mole is 6.022 times 10 to the power 23. So if you do the math and cancel out the same units, and you end up with number of hydrogen atoms, and this comes out to be 2.41 times 10 to the power 24 H atoms. So that's the answer. So I'll give you a question like this, either it could be in gram or it could be in mole, and then I'd ask you to calculate number of atoms in that compound. Now I'll give you another type of problem. Now this time I picked this from the homework. These are all similar problems. Now this is coming from chapter 3, number 39C. It's the 12th edition of Brown-Lemay book. The sample is a sugar. So I have C6H12O6, it's the glucose. Now that sample has 1.250 times 10 to the power 21 carbon atoms. Okay? So this is chapter 3, problem number 39C. So they're saying that you have a sample of glucose having that many carbon atoms. Based on that, you need to find out how many moles of glucose you have, C6H12O6. Okay, starting with this, I need to get this. Again, we're going to do dimensional analysis. 1.250 times 10 to the power 21 carbon atoms times, I need to find out how many moles of atoms I have, or how many molecules of C6H12O6 I have when there are that many carbon atoms. So either way you can do it, that'll be right. But here I'm going to show you there's 6 C atoms per C6H12O6 molecule. You can see here, if I have 6 carbon, that would give me the whole molecule. So 6 carbon atoms is contained in C6H12O6 molecule. So in other words, I can say that 6 carbon atoms makes 1 molecule of C6H12O6. Now I need to know, don't forget that the unit that they're asking for, in this problem they're asking for moles, not just absolute number. If I stop here, you're going to get absolute number of C6H12O6 molecules, but they want in terms of mole. So then I need to do next step, 6.022 times 10 to the power 23 C6H12O6 molecules. That would make a mole of that molecule, a mole of C6H12O6 molecules. Make sure you understand my setup. Now, carbon atoms cancel out. C6H12O6 molecules, C6H12O6 molecules would cancel out, and this give me my final answer. And I calculated this value to be 3.46 times 10 to the power minus 4 mole C6H12O6 molecules. Again, mole represents the big number, and just like 1,000, million. So mole is that. That means I have that many C6H12O6 molecules. Molecules is the label that goes with this formula. So don't get confused between these two. So there will be a question like this. So this is just one of those practice example, and make sure you come up with additional problems. I have assigned additional problems. You go over them, and the same way you can get your final answer. Rather than asking for mole, in a problem I can ask you gram. So what is the gram value? Which is not hard. I mean, once you get the mole, let's use that value, 3.46 times 10 to the negative 4, that's mole C6H12O6 times, since I'm looking for gram, the mole of C6H12O6 molecules would be at the bottom, and gram of C6H12O6 on the top. So I'm assuming that you'd be able to calculate this number because there's 6 carbons, 6 times 12, 12 hydrogen, 12 times 1, and then 16 times 6, then add up that mass would be in here, and that would give you final answer in gram. This is the question, that part D, that I added to this problem. The next type of problem would be on theoretical yield and percent yield and limiting reagent calculation. Theoretical yield, percent yield, limiting reactant. So I picked one problem from the book, which is chapter 3, number 81. And this problem is on C6H6 plus Br2 that gives C6H5Br plus HBr. So these values are given: 30.0 gram C6H6, 65.0 gram Br2, and the question is, what is the theoretical yield of C6H5Br? Theoretical yield is same as expected yield, completely based on calculation. That means when I'm doing this reaction between C6H6, which is benzene, plus Br2, how much I expect to get. One of these will be completely used up and it would give the product. Whatever is completely used up would be limiting reagent. And let me show you these calculations. 30.0 gram C6H6. First you calculate mole. So 78.0 gram C6H6. 6 carbon plus 6 hydrogen masses you get from periodic table. Gram mole periodic table. That gives you 1 mole C6H6. So that gram would cancel out. 1 mole C6H6 gives me 1 mole C6H5Br, and that gives me 0.385 mole C6H5Br. So when I assume that 30 gram of C6H6 is completely used up, this is completely used up, this is the amount of product I'm going to get, this product. I put asterisks because they're asking question about that particular product. So that's the product we are going to get. Now next you assume the same thing for Br2. If 65.0 gram Br2 completely reacts, let's calculate how much of C6H5Br we get. 159.8 gram of Br2. I calculated these numbers, but I'm copying now. 1 mole Br2. Once you understand it, make sure you do the same problem without looking at how I did it. That would be very good practice for your exam. And you should also do additional problems, similar additional problems that I have assigned. 1 mole Br2 giving 1 mole C6H5Br. Now let me explain to you where these numbers are coming from. These are the numbers. 1, 1, 1. It just happened in this case, after balancing, you get 1, 1, 1, 1 reaction. So 1 mole of Br2 gives you 1 mole of this, and that's what we're showing you. In every reaction, you may not have something like this. You may have 2 here and 1 here. Okay, now with this setup, this is what we're going to get. 0.407 mole C6H5Br. So if we assume that 30 gram of C6H6 is completely used up, we get a smaller amount of product. If 65.0 gram of Br2 is used up, I get a larger quantity of product. Both cannot be right. This is the right value. Why? When you get this amount of product, you run out of C6H6, so there'll be no more C6H6 left. That means there'll be no reaction beyond that point. So product is determined by C6H6, and that's why it's called limiting reactant, that limits the product formation. Basically, the reactant that gives the smaller quantity of product is the limiting reactant. So this is the limiting this is the theoretical yield, and this is the limiting reactant. So this is theoretical yield in mole. Now let's get it in gram, because most often we ask question to calculate theoretical yield in gram. So let's now complete that calculation. This is 156.9 gram C6H5Br divided by 1 mole C6H5Br. So that gives me gram, and I'm going to write down the answer, 60.41 gram, 41 gram of C6H5Br. And this is the theoretical yield. Remember that I haven't used any experimental value of product, because we just calculated based on these how much product we expect to get. And that's theoretical yield, and that's the answer to part C. For part D, let's write down part D up here, where you need to get the percent yield. Experimental value is given, and that has to be given for calculating percent yield. 42.3 gram. 3 gram C6H5Br. So percent yield will be given by experimental value, theoretical value times 100. So experimental value is 42.3 42.3 divided by theoretical yield, 60.41 times 100, and that gives you 70%, about 70%. So in exam, you should be ready for doing this kind of problem. So I would ask you how to give you numbers so that you can calculate theoretical yield and percent yield. So make sure you try this kind of problems. Next type of problem would be empirical and molecular formula calculation. Empirical and molecular formula. And there'll be a question on this. So for that, I think this is probably 6th problem type. This is not necessarily the number of, the problems that you get in exam, because sometimes I give more than one question from one type. So this is the problem that I picked. It be from chapter 3, number 51. Brown and LeMay, 12th edition book. The compound is styrene. It's an organic compound. And that has carbon and hydrogen in its composition. Its molecular weight is given, which is 104. If you want to write down in units, it would be 104 gram per mole. Molecular weight is, if you want to write down in terms of gram. Now they gave 92.3%, which is same as 92.3 gram. So 92.3 gram of carbon and 7.7 gram of hydrogen. Of course, I don't have to give you both values. If I just say that styrene is made up of carbon and hydrogen, having 92.3% of carbon, rest would be hydrogen. So 100 minus this is going to be gram of hydrogen. So from here, we first need to get the mole. So 12.0 gram carbon is giving 1 mole of carbon. And that would give me 7.69 would be the mole of carbon. And from here, we can get 1.00 gram of hydrogen. Remember, gram mole, look at periodic table, 1 mole of hydrogen. Actual value is 1.008. I just rounded off to 1.00. So this number is coming from, bottom number is coming from periodic table. This would be 7.7 mole of hydrogen. The rule is, in order to get the ratio for empirical formula, you divide by the smallest value. The smallest of these two in this case, 7.69 and 7.7. So in order to get ratio, divide by 7.69. It's basically 1. So use about 1 here, 1 here. And empirical formula, so you get from this ratio, empirical formula, 1 carbon, 1 hydrogen. So empirical formula is CH. Now molecular formula would be a multiple of empirical formula. So molecular formula will be given by CHN, where N is the multiplicative factor. Now how do I get N value? Molecular weight divided by empirical weight. The molecular weight is given. In this problem they gave you the value of 104, and empirical formula you calculate from carbon and hydrogen, 12 plus 1, that's 13. So this is carbon plus hydrogen. I have 1 carbon, 1 hydrogen. That's an empirical formula. So my multiplicative factor is 8. So molecular formula is C8H8. So there will be a question on empirical and molecular formula. And so these are the two answers that I have highlighted. First you understand how I did it, then you can select other problems and see what they can do in a similar manner. What would happen rather than getting 1, I get a fractional number. Say I may get something like this, 1.5 and 1. You should not round it off to 1 or 2. Rather, if it's 1.5 multiplied by 2, then this should be multiplied by 2. Then it becomes 3 and 2. So these are the ratios at the end. So normally 1.5, so let's keep that in mind. 1.5, that means you have 1.5, so multiply by 2 to get a whole number. If it's 1.33 in this step, where you got 1 and 1, say we got 1.33 and say you got 2 for the other one. This is 1 and 1/3. That means multiply by 3. And you need to also multiply by 3. So this gives you 4, and this gives you 6. So in that case, formula would be C4H6. So keep extra attention to this set of numbers. But we round off to 1 whenever it's really 1, like 0.995 or 1.002. Those are pretty close to 1. So this is all about empirical and molecular formula. The next type of problem that I'll go over is on single displacement reaction. Single displacement reaction. So you have single displacement reaction, and by looking at the activity table, you should be able to predict whether it's a spontaneous reaction or not. Spontaneous means whether that kind of reaction is going to happen or not. Let me give you an example. I think this is number 55, chapter 4a. So this is number 55a from chapter 4. Iron plus copper nitrate. And products are Fe, ferrous nitrate, 2 plus copper. I can easily write down product like this. What is happening here? Iron is taking the place of copper, copper is pushed out, and that's single displacement reaction. This is displacing copper, and copper gets separated. So this is single displacement reaction. Question is, can reaction like this happen spontaneously? How do I know that? Do I need to memorize any information? Answer is no. You can look at activity table. An activity table is given on page, I think, table number 4.5. So look at table 4.5 is activity series. Now if you have a different edition of the book, same textbook, then it may not be table 4.5, then you should look for activity series. Before you take this test, make sure you have the table in front of you, activity table. Now what are you looking at? In activity table, elements on the top are more active than elements on the bottom. If you look at this compound, you'd find that activity of iron is greater than activity of copper. That means iron is strong enough to displace or push out copper. And that's what is happening here. So, in this case, indeed, this reaction happens spontaneously. Because iron sits on the top of copper in that activity series. Remember I said that elements on the top are more active than elements toward the bottom. Let me give you another example. Zinc plus magnesium sulfate. If you expect single displacement reaction, then zinc is going to take the place of magnesium. Then you get zinc sulfate and magnesium will be pushed out. Is it possible? In order this to be possible, zinc has to be more active than magnesium. But in reality, that's not the case. Magnesium is on the top of zinc. So activity of magnesium is greater than activity of zinc. What that means is this reaction cannot happen. No reaction. So it cannot happen spontaneously. So make sure you are ready for answering one such question where you need to look at activity table. For your practice, make sure you do this kind of problems by looking at activity table, which is table 4.5, 12th edition of Brown-Lemay book. The next type of question would be, I'll give you a reaction, you need to say whether there will be a precipitate formed or not in that reaction. Again, here you would be able to look at solubility table. So before you take the second exam, you must have activity table as well as solubility table. So for this you need solubility table. sodium carbonate plus silver nitrate. This is going to be double displacement reaction. I may not give you the final product. So you need to do a couple of things. First, you need to write down the product. Secondly, you need to find out, are those going to be soluble product or insoluble? If it's insoluble, you get precipitate. Precipitate, that's what you need to examine here, plus the products. This is the double displacement reaction. So let me write down why you have this formula. Because sodium is +1. Remember, carbonate is coming from the acid carbonic acid, H2CO3. My pen is not working, so let's try another one. CO3 comes from H2CO3 by knocking off 2 hydrogens, so you get CO3 2 minus. So I know from acid, that's CO3, we have 2 minus. And this checks out. 2 goes down here, so you get Na2CO3. Now, you soon understand that why I'm writing down like this. Nitrate coming from HNO3 by knocking off 1 hydrogen. So NO3 is -1. And silver, this is the neutral compound. If it's -1, silver has to be +1. Because 1 minus 1, that's 0. Okay. This would help you to predict the product of the reaction. This is a double displacement reaction. Sodium takes the place of silver, silver takes the place of sodium. So let's now switch. Sodium taking place of silver. So let's have sodium plus, and these numbers don't change, the pluses and minuses. This is +1. +1 goes with nitrate, NO3, which is -1, plus silver takes the place of sodium, so silver +1, and that goes with CO3 2 minus. Okay. So first write down side by side before you write down the formula. 1 and 1, so the 1 goes down here, 1 goes here, so get NaNO3 is the right formula. And here, these 2 comes down here, 1 goes here, so the new product is silver 2, CO3. So why I wrote down like this? I wrote down like this so that I know pluses and minuses carried by different species in this compound. And now I predicted the final products by switching both positives. Sometimes you get the same answer by switching the negatives. So let's now delete this, make it more clear. Now you need to look at solubility table to find out whether both are soluble or not. If you look at solubility table, you find that this is soluble in water. So there will be no precipitate because of sodium nitrate. On the other hand, you'd find this is insoluble. So there will be a precipitate. So there will be a precipitate formed in this reaction, which is due to silver carbonate. So I'll give you a problem in which you need to predict whether there will be a precipitate, and precipitate is due to what compound. The next type of problem that I'd like to go over is calculation of ion concentration from a compound. So concentration of ions. This is number 69 from the same chapter. So 0.15 molar K2CrO4, and we need to find out what molarity of different ions we have. that many molar K2CrO4 has, if you just look at one molecule, you have 2 K plus per molecule and 1 CrO4 minus. So that makes it simpler. If I have 1 molar, I would have 2 molars of K plus, 1 molar of CrO4 minus. If I have 0.15 molar, it would be 0.15 times 2 for K plus, and 0.15 times 1 is going to be CrO4 minus. So I'm just going to do one such calculation, and because this would be pretty straightforward. So you'd have 0.15 molar, if you want to show dimensional analysis, K2CrO4 times 1 molar K2CrO4 would have 2 molar of K plus. And that would be 0.30 molar K plus. So this would be straightforward. Next type of problem would be oxidation reduction reaction. Oxidation reduction reaction. I'm going to give you a reaction, in this case nitrogen plus 3 hydrogen, giving 2 NH3. You need to find out which one is oxidized, which one is reduced. Now let me remind you, oxidation means increase in oxidation number. Reduction means decrease in oxidation number. For pure elements, oxidation number is 0. This is also pure element, is 0. But for the product, it's not 0. Now how do I find out oxidation number? Hydrogen is plus 1. Each hydrogen is plus 1. Since there are 3 hydrogens, plus 3. This is the neutral molecule NH3. So this has to be minus 3. Because they must add up to 0. So now I know that nitrogen is minus 3. Each nitrogen is minus 3. I'm writing down each value on the top, because that's what is called oxidation number, the number associated with each element in a compound. So what is happening to nitrogen? Nitrogen changes from 0 to minus 3. So it's decreased. So reduction had happened here. In case of hydrogen, starting with 0, it's increased to plus 3. Plus 1. You don't count the total value, you count the top numbers. These are oxidation numbers. By definitions, oxidation numbers are the positive and negative on each element. So this has increased, so this has undergone oxidation process. If there is no change, then that means there was no oxidation or reduction reaction. The next problem that I would like to go over would be dilution problem. This is number 75B, chapter 4. Basically, this is the problem. Let me explain that to you. You have 3.00 liter of 1.50 molar sugar. And you need to make, from here, 350 ml, you need to get 350.0 ml of 0.100 molar sugar. In our lab experiment, we often make diluted solutions, Now, our common sense would say that this is a concentrated solution. Take a little bit of dilute concentrated solution from the top, from this, and that's the concentrated solution, and add water so that you finally get 350 ml of 0.1 molar sugar. Okay, so this should be 350 ml. So basically you get a little bit from the concentrated solution and add water so that you finally get 350 ml of 0.1 molar sugar. But the question is how much of the concentrated solution you need to take here before you add water. That's what we're going to figure out. So let's now do this kind of setup. Molarity 1 equals to 1.50, which is the concentrated one. Volume 1 that I need to transfer from here to here, I don't know yet, and I need to calculate that. So I have a question mark. So I need to find out what volume I need to transfer. And molarity 2, my intended molarity is 0.100, and the volume is, intended volume is 350 ml. So first you write down like this before you solve the problem. So let's do the setup. Molarity times volume, let me write down here. V1 M1 equals to V2 M2. Let me tell you what's happening here. If this is in liter, so liter times moles per liter, that gives you moles. That means I have a moles of sugar at the beginning would be same as moles of sugar at the end. If you just focus on this beaker, you'll see that. Whatever number of moles of sugar I got, by adding water, it doesn't change. That's why I can apply this. V1 M1, which refers to this area, or this volume, that's the moles of sugar that I took, and then by adding water, that mole didn't change. So moles per liter, moles at the beginning equals to moles at the end. This is the beginning, this is the end. So then I can do the problem. Now let's now solve it, and I'm going to calculate V1 will be given by V2 M2 over M1. Even though I've shown you this calculation with liter, you don't have to get liter. You have ml and ml because they would cancel out. So rather than doing that extra step of converting to liter, I'd leave it as ml, 350.0 ml times 0.100 moles per liter, divide by, molarity 1 is the concentrated one, and this would give you 23.33 ml, because molarity cancel out. That means you need to transfer 23.33 from here to here and add rest water. So how much water you need to add? So add, this would be 350, because you need to get 350 ml minus 23.33, that we add this much of water, which is 326.67 ml. So basically you take 23.33 ml from concentrated solution and add 326.67 ml of water to get that solution. And there will be a question like this in exam, and make sure you know how to do it. Next problem would be titration problem. So titration problem. This is from chapter 4, I think it's number 82, chapter 4, 82. Now first you need to write down a balanced reaction. 2HCl plus BaOH2 giving BaCl2 plus H2O. So I already balanced it just to save our time. Now, if you're wondering how we got these products, Ba is plus 2, OH is minus 1. Let me write it down, because at the beginning it could be a little bit harder for you. This is Ba is plus 2. Each OH is minus 1, coming from H2O. Original compound is H2O. If you knock off one hydrogen, you get OH minus 1. Now in double displacement reaction, hydrogen takes the place of Ba, Ba takes the place of Cl. So this is how you get BaCl2. This is Ba is plus 2, Cl is minus 1, and this is coming from H plus and OH minus. Then I balanced it. That's how we got 2 here in front. Always you'll have to begin with balanced reaction. Now what is given in this problem is 0.120 molar HCl, and what volume you need to take. So you are titrating with HCl. This is what you have, barium hydroxide. And from the top, you are adding HCl. And the question is, what volume of HCl you need to add so that 50.0 ml of barium hydroxide with molarity of 0.101 will be completely neutralized. Okay, so this is the given information. You have 50.0 ml of 0.101 molar barium hydroxide. So we need to know how many volumes, what volume of HCl we need to add. And we're going to show you that calculation. So start with 0.101 moles per liter. 1 moles BaOH2 per liter times 50.0, that's ml, we have to change it to liter, 10 cubed liter, and then we can the liter will cancel out. Then you'd have 1 mole BaOH2. 1 mole of BaOH2 is 2 moles of HCl. That we get it from this. 1 mole reacts with 2 moles of HCl. That's what we're showing you here. 1 mole of BaOH2 reacts with 2 moles of HCl. And then we need to have 0.120 moles per liter. Keep this in mind. We're introducing this. 0.120 M means 0.120 moles per liter. So that's that many moles per liter of HCl. I need to use it here. So a mole of BaOH would cancel out. This would give me moles of HCl. Then I'm going to use this information. 0.120 moles of HCl. Moles HCl, that gives me a liter of solution. So, after all these unit cancellation, this is what I end up with. 0.0842 liter, and then you can change it to milliliter. 1000 ml makes a liter. I think in the book there they expressed answer in milliliter. So that's 84.2 ml of HCl. So this gives you answer that how many ml of HCl you need to add so that this much of barium hydroxide is completely neutralized. And that'd be a question like this from titration, and make sure you go over this problem as well as other problems. Now the other types of problems I'll ask you about weak, strong, and non-electrolyte. Now electrolytes are the solutions that would allow electricity to pass through. So basically these are the strong electrolytes break down into ions. So like KCl, NaCl, most of the sodium potassium compound, they break down 100%, making it a strong electrolyte, would allow electricity to pass through. Weak electrolyte, mostly organic acids. Organic acids are not as strong as inorganic acids. They will break down only partially. Say out of 100, maybe 10 of them would break down. On the other hand, in case of KCl, out of 100, all 100 would break down into K plus and Cl minus. What about non-electrolyte? Non-electrolytes are sugars. If I add any kind of sugar, it could be table sugar, which is sucrose, it would not break down at all. So that would be non-electrolyte. That means it doesn't help electricity to pass through. Next type of question would be what we call spectator ions, and this will be the last type of problem that will be on the test. So spectator ions and net reaction. By going over this problem, which is chapter 4, number 39, so I'm going to write down for the reaction 2HBr plus CaOH2. Again, this is a double displacement reaction giving CaBr2 plus 2H2O. Now, if products are not given in the similar manner, remember I showed you before with positive, negative, you can predict the products and then you can balance it. From solubility table, we find out whether these are soluble or not. So this is soluble. AQ means aqueous solution, aqueous solution, aqueous solution, AQ. And this is a liquid, H2O. It would remain as H2O. Now, the ones which are AQ, they would break down into positive and negative. And so let's write down the broken fragments. 2H plus, these are aqueous, plus 2Br minus, minus aqueous. Calcium would break down from OH minus, so you get calcium 2 plus, aqueous 2OH minus, aqueous. So that's, I'm done with the reactant side. And the product side, this is aqueous, so we need to break down the 2. Calcium 2 plus, aqueous 2Br minus, aqueous. These are the broken fragments, 2H2O. So the key thing is, if you see something solid, liquid, then leave it as it is, or even a gas. The rest, whatever you see AQ, break it down if it's a positive, negative type of compound. Okay, now how do I get spectator ion? The spectator ions are those ions which do not take part in a chemical reaction. Look at here. In other words, they remain intact. Nothing happens to them. Calcium. On the reactant I had calcium. On the product I also have calcium. Nothing had happened to calcium. It didn't take part in this reaction. Just like a spectator watching a football game, they are not players. They are not playing the game. Similarly, these are the substances, they don't take part in the reaction, for which you have them both in reactant side as well as product side. Nothing had happened to them. So, spectator ion in this case